In all physics institutes, I think the research atmosphere is similar. You have lunch with colleagues that work on similar things, but not too similar. And that's when you discuss typically physics of what papers came out today and different areas, and you see if different ideas from different areas could be relevant for yours, and you get inspired. And then you go back after lunch, and then you discuss with one or two people that are working on the same things that you are working on, and then you really try to push really your projects. So as long as you have a critical mass, it's not like you need a perimeter is a top luxury, right? I mean, perimeter, like hundreds of people and so on. So it's from that point of view of being able to discuss many more topics is really the best. There's nothing like perimeter. But to have an amazing atmosphere, you need a critical mass. You need like 4 people to go for lunch with that work on relatively similar topics. And then you need 1 or 2 people that work on what you are working on.
The guest of today's podcast is Dr. Pedro Vieira. He is a theoretical physicist working on integrability, holography, and matrix models. In the past, he has also worked on Bootstrap techniques. So let's talk to Dr. Vieira about his work in physics and listen to what he has to say. So, Dr. Vieira, welcome to the podcast. Nice to have you.
Thank you. Thanks for having me, Hassan. It's a pleasure.
So before we talk about anything else, can you tell us about the projects that you are working on nowadays?
One project that I'm working on is actually very, very easy to describe. It goes back, I should know this, but maybe 200 years or something like that, which is what is the minimal area problem? So this is a very, very old problem. Imagine you have some piece of wire and you dip it in soap, and then you take the piece of wire out, like a circle or a square, any shape, and there is a surface, a soap bubble surface, that's the surface with the minimal area. So a very basic question in mathematics is, what is the minimal area for a given shape? So if I have a circle, if it's a plane, the surface is just flat. But if I have a complicated shape, the surface is going to be very complicated. So one thing I'm trying to understand, so of course this is, as I said, a very, very well posed problem. Actually, mathematicians work on this problem, trying to understand, are we certain that such surface exists? When does such surface exist? In which dimensions do such surfaces exist? And so on. But physicists also care about such problems. They appear when we study, soap bubbles, for example, but also string theory, because string theory describes surfaces, which are strings moving in space-time and so on. So it's a problem that is relevant all the way from string theory to soap bubbles. And so I'm trying to understand that problem. And in particular, I'm trying to understand how can we study areas of minimal surface, what's the surface, what's the area of these minimal surfaces, without knowing the shape of the minimal surface. Because often knowing the shape of the minimal surface is too complicated. I mean, if you give me some polygon wire that is very complicated, there's not too much hope that I'm going to find the shape. What about finding just the area? You tell me, I want to find the optimal surface that ends on some pentagon or hexagon that's all twisted in space. And you ask me, please give me the area. I think it should be possible to compute this area without knowing the shape. So that's something I'm very much actively working on with some colleagues. So that's one problem that, as you see, it's very easy to state. You can say it's a problem either in mathematics or in physics. Maybe I'll stop here and see if you have any questions or if you want to go on. I have many projects, of course. So this is one of them. It's the one I worked on yesterday and that I'm going to work on today. So it's probably the one freshest in my mind.
So this problem, as you said, that it's quite easy to explain what the problem is. And someone who is relatively familiar with how physics and maths works would tend to guess that there must be some significant progress that has already been made on this problem. So how much progress has been made on this problem already?
So there are many approaches to this problem. One, as I said, the idea is find the surface with the minimal area, the optimal surface. So this is a field of mathematics called calculus and variational principles that's very well studied. It's a field that was developed since Lagrange, trying to understand what equations describe optimal things, be it the movement of particles or shapes of minimal surfaces like I described. So this is very well understood. And indeed, one of the ways of studying this problem is solving so-called differential equations. So equations that give us the shape of these surfaces. These are equations which are a bit different from differential equations giving movement of bodies, because movement of bodies, typically we specify the initial conditions. I throw a rock and I say, what's the initial position and velocity? And then I evolve this differential equation to find out the shape of the particles. Or when I study cosmology, I give the initial conditions for the universe and let it evolve, and I study the differential equations that govern the size of the universe. Here, when finding the surfaces of soap bubble, we don't give initial velocities, but we give what we call boundary conditions, global boundary conditions. We say, what is the shape all around the surface? We say, where's the wire? And then we evolve the equations, if you want, inwards, and we find the optimal shape that goes inside that fills in this wire. So that, I would say, is the brute force way of doing it. You give me some piece of wire, and I just compute it. I either dip the wire in soap and take it out and measure, or in the computer, I optimize solving these differential equations by what is called relaxation, which is you start with some wrong guess and let the computer get a better and better and better guess until you get the optimal surface. Now, this is one way. And for me, it's like the lab, is that whatever method I'm going to come up next, I have to contrast it with this. I'm going to produce new ways of computing, and then I always have to check. If I say, oh, I have a better way of computing, great. So compute it by brute force first, get a number, 4.23. Does your new method give 4.23? Good. So what would be new methods? One is sometimes you can find these surfaces analytically. If you are lucky enough, if your boundary conditions are simple enough, perhaps you can just solve the differential equations. You don't need a computer. You just solve it with pen and paper. Such examples were done. There is a very famous polygon known as the Schwarz quadrilateral. That was solved in the beginning of this minimal surface problem. It's a particular shape with 4 edges that is very symmetric, and then you could solve exactly the shape of this surface. There is some funny square root with 8 zeros, and you integrate that square root or inverse square root, and you get the shape of this surface. Recently, people in the study of ADS-CFT, that I'm sure it's a topic we are going to cover at some point today, which are these dualities between gravity and quantum mechanics, people like Aldai and Maldacena, they understood that such surfaces also appear when studying the scattering of gluons. Okay, the analog of photons for the strong force. And these gluons, it turns out that studying the scattering of these gluons is also related to a minimal area problem. Namely, when you study the scattering of gluons in the so-called strong coupling regime, the regime where quantum effects are very strong in these ADS-CFT scenarios, you have, if you want to study, like, for example, 4 gluons, 2 gluons coming in the past, 2 gluons going out in the future, you also need to consider a quadrilateral, but it's a quadrilateral where the wire is put at the boundary of this spacetime, very far away at this boundary of this anti-de Sitter spacetime. So here you have 2 examples, the Schwarz quadrilateral, studied maybe in 18 something, I don't know. And then the Aldai-Maldacena quadrilateral, the quadrilateral that is at the boundary of ADS and whose minimal surface computes this scattering amplitude for gluons. And now if you ask, can I take these quadrilaterals that are known analytically, and can I find not only quadrilateral, but any polygon, and not only at the boundary of ADS and not only in flat space, but all the way in between? Can I find what's the minimal area of any polygon? And the answer is we don't know how to do it. This has not been done. But what we are trying to explore is the notion that these surfaces that often I think of them as strings because they are really like the shape of a string moving in space-time draws some surface, are integrable. That means that their dynamics is exactly solvable. You can imagine that this surface is like some piece of material, and the ripples, the waves, the fluctuations of this surface are integrable. And that is very powerful. It means that when you change the shape of this surface, there are lots of symmetries and lots of conserved charges. These ripples propagate and they move around on this material, but they don't move around in a random way. They move around in a very organized way. And it's this power of integrability that I'm trying to tame in order to compute these general polygons for any number in a very generic sense. In the context of gluons, we had done this before in the past, maybe 10 years ago, with Fernando, Juan Maldacena, Gaiotto, Amit Sever. I had studied this problem of trying to understand these polygons in that particular context of polygons that end on the boundary of de Sitter. And that's exactly what we did. We managed in that, like this 10 years ago, to compute the area of these polygons without knowing their shape. But as I said, it's for very special polygons. It's polygons that end on the boundary of this de Sitter space. So
So
I was thinking, I want to study this much more generally. I want to understand much more how to understand areas of surfaces without seeing the surfaces.
I see. So, for example, if we look at the diagrams that are behind you, are they related to four-gluon exchange or something else?
This diagrams there. Yeah, so what they are. In short, they are. But in detail, the way it works is the following. So when you have these surfaces, it seems to be the case that studying a general surface, imagine you have some surface that's very complicated. Its topology can be very complicated. So here in the back, I have some examples where I have like two strings moving in, they interact and they split. So it's like a topology of two pair of pants that are glued together. Now, studying pair of pants that are glued together, there are a lot of parameters. They can be fat, thin, twisted, not twisted. It's very complicated. The geometry of these surfaces can be very intricate. So it seems to be very convenient to break it apart, to cut this surface into smaller building blocks. And it seems like the building blocks that we want to cut this surface in are hexagons or triangles. And well, hexagons are not triangles, so it might seem strange why I'm saying hexagons or triangles. So let's just say hexagons. So if you look in the back here where I'm pointing, you can see that there is an hexagon here. If you count one edge, two edges, three edges, and if you count the other three, it's six edges. So it turns out that if you have some surface, you can somehow always cut it, these string interactions, into hexagons. So it seems like perhaps a way of studying this problem is understanding better these hexagons and how to compute them and glue them together. And this could give us a new way of thinking about this surface. But that's a very technical point, though, if we can go there if you want. But
Okay. So before we talk about some of the topics that you have worked on, can you tell us a bit about how you got interested into physics when you were young?
I think it's not very different from probably 99% of people that went into physics. It often happens that you love math. So there is a subset of people that just find math very appealing. And if you combine that with having a good high school teacher in physics, then it's a deadly combination. I think it's irresistible because the combo of the two, if you love math and your physics teacher is not good, maybe you will end up doing something else. But if you love math plus your physics teacher is good, it's the combination of both is so fascinating. It's so amazing that it's kind of irresistible. Plus, in my personal case, I have many people in my family that did math. Either they taught math in high school or taught in university or wrote math books for students, my grandmother, for example. So I had lots of mathematicians in the family. And I suspect probably unconsciously, I also wanted to do something a little bit different. So I think that it was a combination of those factors. Yeah.
I see. So for some people, actually for a lot of people who, do theoretical physics, they mentioned some book that they read when they were young. So was there a book in your case as well that you read?
Uh, the usual books. I've seen a couple of your podcasts, and people more or less always say the same books. So for me, it was not very different. Again, Hawking. There was a book by Einstein, some book by Feynman. It's more or less the the standard
Okay.
set of books. Yeah.
Okay. So one of the topics that you have worked on is integrability, as you were mentioning, some minutes ago. So can we start from what is integrability? I mean, how to explain the concept of integrability to people who are not familiar with it?
Mhm.
And, as when you're on it, can you explain what is the difference between classical integrability and quantum integrability? Because people use those terms when they talk about integrability.
Okay. So integrability in practical terms just means solvability. So we say a theory can be solvable or not. By solvable, typically the standard we mean is you can go to the blackboard, people are sitting in front of you, and you say, okay, let's go. And you start, ta, 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 and you say, and therefore the solution is, and you write down a formula. By non-solvable, I mean that you need a computer. It's not like you cannot plot the result or compute the result, but it's not something that you can do in the blackboard with people, in a discussion with people. So that's the difference. Of course, you could say it's not a huge difference. I mean, but it's a difference. And having examples of theories that you can solve exactly, it's very important because often for some things, having an exact analytic solution is crucial if you want to really study detailed properties of certain limits and you want to ask, are there singularities or are there problems with this quantity in some regimes or not? It's very good to have exact solutions because with numerics, you are never certain. Oh, did I put things right in the computer and so on? So it's very, very important to have exact solutions. So integrability in short just stands for exact solutions for me. But then you could ask, when can you have exact solutions? Well, what does it mean to have solutions that I can solve exactly for quantum problems? And that would be what you call quantum integrability. And when can I solve classical problems? And that's the one you would have classical integrability, like you said. And different people will give you different definitions because there are many things that almost always, if you have thing A, it implies thing B, and so on. Okay, so let me then tell you a little bit. So one property of integrable theories is that lots of things don't change. There are lots of conserved charges. So I remind you that some things that don't change is like energy. If you have if some things have some energy, energy can be transmitted from things to things, but it's constant. Energy is constant. If space-time is not changing, energy doesn't change. Momentum, the same. If you have a spaceship moving in space, moving to the right, unless someone touches it, it keeps moving to the right constantly. So those are the most known charges. It's energy and momentum and angular momentum. If things are rotating, like in a solar system, they stay rotating. So if you look at the solar system, that's what you have. You have energy, you have angular momentum, you have some asteroids passing sometimes, and that's it. You have momentum, angular momentum, and energy. In integrable theory, you have infinite amount of charges, infinite amount of conserved quantities. You don't have just these three, you have a tower of them. You have many, many of them. And in the same way that momentum, if you tell me I have a rock that is moving, all I ask you is, what is the velocity of the rock? And where did it pass by? And you tell me these two things, and I immediately know what the rock is moving. If you have a string moving in space, it's much more complicated because the string has some size, right? So it can be vibrating, it can be moving in very complicated terms. So you could say just knowing what's the velocity of the string is not enough because it's different to be moving in a boring way or to be moving in a dancing way. It's very different. So you need to give me more information. And so it turns out that for the string, there is such information. The string is integrable. There are many more charges you can conserve, not just the momentum, but many more charges you can consider. And therefore, you can describe the classical movement of the string very powerfully. And that would be an example of classical integrability. It's an example where you just study the classical motion. There was no quantum mechanics in this discussion, actually. So far in the podcast, we almost never mentioned quantum mechanics. So the string is just moving, following its dynamics, its equation of motion, and it has many conserved charges. And because of that, we can study its movement analytically. Now, do all strings move with these many conserved charges? It depends. If the space-time where they move is simple enough, like empty flat spacetime, or these spacetimes that are called anti-de Sitter or hyperbolic spacetimes, then yes. But if they move in a very complicated spacetime, which is not as symmetric as the ones I mentioned, then no. Then the string moves in a complicated way. So to study some strings, I can give a lecture. To study other strings in other complicated spacetimes, I need a computer. And I need to first run some simulations. So that would be an example of classical integrability.
I see. So suppose that we have a system that has like n degrees of freedom. So right. So in order to specify the state of that system, you need n numbers, right?
Okay.
For that, to solve that system, you don't need more than n conserved quantities, right?
That's right.
So it means, so if you have n conserved quantities for a system that has n degrees of freedom, would you call that integrable?
I would not. Some people would. So, okay, so because of the following, I would say that to be integrable, you need not only to have enough conserved charges, enough symmetries, but they need to be simple enough. If they are something very non-local and very complicated that in practice you are never going to write down, then their existence is useless.
I see.
So it's more or less always the case that you have conserved charges, because ultimately, forget about classical physics. Say classical physics is a limit of quantum physics, right? And what is quantum physics? What's the evolution in quantum physics? You have your wave function that describes the quantum state. And then you have an Hamiltonian, which is just some big matrix that acts on this wave function and that involves the wave function. So it's just some linear operation that tells how the wave function moves. Okay, so that's quantum mechanics. It's just some wave functions evolving linearly in time. And these conserved quantities in this language are what are the operators that if you evolve and you measure this quantity, things are the same before and after evolution. And we say when things are the same before and after, we say they commute, meaning we can measure the energy before we evolve or after we evolve. And this commuting, the fact that we can permute both and the result is the same, we say that the energy or the momentum, for example, commutes with the evolution, which is the Hamiltonian. And then we say when they commute, we have a conserved quantity. But the Hamiltonian is just a matrix. So once I diagonalize the matrix, I can always find matrices that commute with it, of course. And you can find as many matrices as the size of the Hamiltonian, right? It's very easy. Except that these matrices that you find, when you translate back to a physical basis like position and velocities, they would be highly crazy objects that they will be impossible to realize and to measure.
I see.
So from that point of view, it's a bit useless. So just saying the number of charges is not enough. They have to be something relatively simple, like the momentum of the particle. You take a few pictures and you tell me what's the velocity of the particle. If the charge is so complicated that you take a bunch of pictures and you cannot tell me what the charge is, then that is a bad charge.
I see. So you explained what classical integrability is. So how do you describe quantum integrability then?
Uh, so um, let me go back to classical integrability and add one more thing about classical integrability, because once I add that, quantum integrability will be easier to explain. So we have these strings that, as I said, they are moving, and their description, their movement is simple enough that we can study. So what's going on? Let's zoom in on the string, and the string is moving, so it's drawing some shape. It's a surface. And so on the string, you have waves. You have small deformations of the string that are moving on the string. So imagine the string is some big piece of cloth, and there are some ripples on this cloth that move, some fluctuations, and then they hit each other and they bounce back. And there are many such fluctuations on the string, many such excitations. Like in a string of violin, you can create some waves that move and can hit each other. And these waves that describe this evolution of this material of the string, when they hit each other, when two waves hit each other, they bounce back. When three waves hit each other, in principle, very complicated stuff could go on. In principle, three particles hitting each other, they could produce a mess. When you have these very, very many conserved charges, what happens is that when three particles hit each other, when three fluctuations hit each other, in the future, they produce three fluctuations. Not two, not four, not six, not a mess, but they produce three again. And that you could think is very weird. Why would three particles move? They are all colliding at the same time. Boom, boom, boom. You can imagine three collisions, like three asteroids, and they collide at the same point. Why in the future they produce something nice? Why don't they produce a mess in the final state? And the reason is related to these charges, actually. Because these charges, for example, the fact that the energy is conserved is because you have translation invariance in time. Namely, if you do this collision of asteroids today or tomorrow, the result is the same, right? And it's this constancy, the fact that things don't change if you change time, if you do today the experiment or tomorrow or in 1 year, the result, it doesn't matter. It's this constancy in time that gives the constancy in energy. The fact that you can do the experiment here or to the right or to the right or to the right of it, it's what gives constancy of momentum. It's translation in space. So if you have these three asteroids meeting at a point, you can translate them all in space or in time, and the result is the same. But you see that they still meet at the same point. If they were meeting at the same point, and if you push everyone to the right or push everyone to the future or push everyone to the left, they still meet at a point. But now imagine that you have not just energy and momentum that allows you to translate things in time or in space, but you have more charges, the ones that I said integrable theories have. What can you do? You can also translate these particles, but now different particles are translated by different amounts, which is something very weird. And now, before, the three of them were tuned so that they would meet at the same position. Now you translate them, and now they meet in different positions. Maybe asteroid 1 and 2 meet, then 2 and 3, then 1 and 3 later. And because of that, you relate processes where you scatter three particles with a sequence of simpler processes where you scatter two particles. And that is, in essence, perhaps the most fundamental aspect of integrability, is the existence of these charges make it such that in a physical process, you can break it down into simpler building blocks. I just gave you an example. The scattering of three particles, something that typically is very complicated, because of these symmetries, can be described as if it was a sequence of two particles meet, then two particles meet, and then two particles meet, right? So as if they were just meeting in pairs. And the complication of all the three particle and four particle and five particle and six particles, it can all be broken apart into smaller building blocks of two particles. Now, I like this description, and I like this description also because it translates immediately to the quantum level. Everything I said, describing these classical ripples that move in classical pieces of cloth or water or something, translates to quantum mechanics. Just replace classical ripples of cloth by quantum particles. And now you can have quantum particles that meet, and again, it will be a mess if they collide, three electrons. But if the theory is such that I can separate them, then I can study all this physics by the fundamental building block, which is how two particles meet when they meet. And it's the fact that physics can be broken apart into these very small building blocks. When this happens, it is often the case that we can solve the theory. Now, can we solve some theories where this doesn't happen? Yes, but typically this breaking of physical quantities into smaller building blocks, which in technical terms we call factorization, this factorization is what ultimately leads to a theory being integrable. In other words, exactly solvable.
So you said that if a particular system is integrable, it needs to have an infinite number of conserved charges, right? So if there is a system and somebody is able to find this infinite number of conserved charges, then of course that theory will be that system would be integrable. But
Mhm.
is there a way to prove that a system is integrable without finding all of these infinite charges?
I would say, imagine you do the the scattering experiment I just said. Prepare three particles and send them against each other in a way that they will meet at the same point in spacetime. Right? So one particle can be quiet in the middle at zero velocity, so it's just standing there. And you put two particles, one on the left, one on the right, and you send them with the same velocity towards the middle. So then they will hit the middle particle. Right? The three of them will meet in the middle. If the final outcome of that experiment is the same, one particle in the middle, one going to the left, one going to the right, for sure these charges are there. Because there is nothing that would guarantee. A priori, you would get a complicated state. All you need is that the total energy and momentum are conserved. But the individual energies and momentum being conserved, that's a priori not required at all. And so if you do such simple scattering experiments, and if the velocities of the particles in the future are the same as the velocities of the particles in the past, for sure these charges are there. You just need to look a bit harder.
I see. I see. So one area where you have worked quite a lot is using, integrability in holography. And when you study integrability in holography, what kind of questions are the major questions that you ask there?
So I mean, one of these situations that I feel like I should give a little bit of background, maybe to be
Mm-hmm.
able to, otherwise I feel super that I feel
Okay,
like I'm going to jump to something very advanced. So let me
sure.
perhaps start by saying that one of the areas of research that a huge portion of the string theory community is interested in is this field of holography that you said. So holography is the idea that perhaps a way of describing quantum gravity, which is this dream of physicists of finding a theory that unifies quantum mechanics and gravity, that perhaps quantum gravity is described by just a theory without gravity and just quantum mechanics in one less dimension. And we call this an hologram because of that, because it's as if there was a theory at the boundary of the universe, like a screen at the boundary of the universe that would describe everything that is inside. So it's a possibility that perhaps that's how the universe works. But what we are doing, what people have done mostly so far, is explore in toy models, in toy theories, what would be the consequences if that were true? If it were true that I could perhaps describe quantum gravity by just describing quantum theory without gravity as a screen at the boundary of the universe. And this idea that is called the holographic principle, and that Juan Maldacen in 97 made precise and said, so it's just not just words. Here is an example of a theory that where there is quantum gravity, and it should be the same as this hologram, this theory in one less dimension that is a quantum theory only. And when you say two things should be equivalent, it's like saying two languages are equivalent. And this is fine. Okay, it's true. Most languages are equivalent to each other, but you need a dictionary, right? And so if you don't have a dictionary, it's more or less useless to know that that there is a map between two things. And so when you have this duality, when you have this holographic duality that you can describe quantum gravity as a quantum theory, then you want to know what should I compute in quantum gravity, what should I compute in the quantum theory, and which ones should be the same, and how can I test this duality. And the simplest thing you could imagine is what is the spectrum of the two theories, which means what are the energy levels, the energies of the system, right? So the quantum theory, you can think of like an hydrogen atom. It has some energy levels, some possible energies, some possible configurations. String, you have string in this space-time. There are a bunch of strings moving and they have their own energies. And it turns out that this dictionary says the energies of these strings, right? We spoke about these strings moving in an integrable way. The energy of these strings that move in this integrable way should be the same as the energies of the quantum system that appears in holography, which goes by the name of n equals 4 super Young-Mills. It's just a name for this quantum theory. And so a key challenge that was open when I was a PhD student was compute the spectrum and check if this is true. Because these dualities are conjectures, so they are by no means obvious. So, of course, they are true conjectures. No one doubts that they are true. But they are very, what makes them most powerful is also what makes them hardest to check, which is that they are dualities that when quantum gravity is in a regime that we know how to compute, that should be dual to the quantum theory in a regime that we don't know how to compute, and vice versa. In technical terms, we say they are weak-strong dualities. They map easy in one theory to hard of the other theory and vice versa. And because of that, it was very hard to check. People said the spectrum of this theory, the energy levels of theory A is equal to the energy levels of theory B. And this was important to test. It would be a very strong test of these holography ideas. And a priori, as I said, it would be impossible to compute if it was a normal theory. But it's not a normal theory. It's an integrable theory. And the way to think is that the dynamics of this string, the way these strings vibrate and fluctuate, the possible energies of this string are constrained by integrability. It's not anything goes. And we could try to use integrability techniques to study the possible movements of these strings and to study the possible energies of this string. And so this was an ongoing project. I remember of hundreds of people, that it was a very, very hot topic when I was a PhD student, and people were just trying to compute this spectrum. And typically what you would do is you would compute what you could. You would say, let me study in the quantum side, and you would compute in the so-called weak coupling regime. Now let me study in the gravity side, and you would compute in the so-called strong coupling regime. And you would start getting hints of this function, the energy function that should interpolate between the two. And the more hints you got, the cleaner, the more obvious it was that they should eventually be the same thing. But it was very hard to find the exact result because you really needed to use quantum integrability to the fullest. So that was the problem that we solved in 2009 with Kazakov and Gromov. We understood how do we tame completely all these particles of the string, that there can be many of them. It's a quantum system. They are popping up, and it's a very interesting state. How do we describe all these particles in order to compute the energies? And we did it, and we saw that indeed the energies of the states of the quantum system, as the coupling becomes stronger and stronger, they start behaving more and more as strings and classical strings moving freely in space. So that perhaps that was an important milestone in our understanding of these ADS CFT dualities, I would say.
Well, so you described a work of yours that I wanted to discuss in much more detail with you. So since you have started talking about it, so let's come to that particular work of yours. So this work that you did, I mean, as you said, that you were trying to figure out the energy levels of string when the string moves in a particular space-time called ADS5 process 5, which is 5-dimensional sphere times 5-dimensional ADS5. And as you said that we know that it is dual to a theory called n equals 4 super Young-Mills that has supersymmetry, and it also has a symmetry called conformal symmetry, right? And you said that you were trying to figure out the energy levels of the string when it moves in the ADS5 process 5. And due to the ADS CFT dictionary that you mentioned, it translates to something called the scaling dimensions of operators on the on the super Young-Mills side. And if you want to correct the quantum mechanical corrections to the energies on the ADS side, that translates to something called the anomalous dimension, because though they are generated by quantum mechanical corrections. So I have quite a lot of questions regarding this work. One question that a person who is naively familiar with n equals 4 super Yang-Mills may have is the following. So someone may say that we know that in n equals 4 super Yang-Mills you have too much supersymmetry, and because of that you don't have quantum mechanical correction. So how can you have anomalous dimensions there? So how would you answer that? That's the first question.
So the answer is that the small flaw in that statement is that
Mm-hmm.
the theory can be very supersymmetric, but that only translates into the quantities being very simple if the quantities are also supersymmetric.
Okay, I see.
So if you compute something like what's the energy of the vacuum, that is very easy. If
Mm-hmm.
you ask what's the correction to the action of the theory, to the Lagrangian of the theory, how is it corrected? It's not corrected. It's very simple. So that's because you are asking supersymmetric questions. If you are asking what is the interaction of so-called supersymmetric particles or BPS particles, that's not corrected.
Okay.
But data is okay for some quantities, but for most quantities, for example, if you send two gravitons against each other and they go into two gravitons, that's not supersymmetric. That quantity is not supersymmetric. So even though it is in a supersymmetric theory, the quantity itself breaks supersymmetry, and therefore its behavior is it's not trivial. So the quantum effects, so uh, they are simpler. The results are simpler than in a theory that is not supersymmetric, but they are not trivial. They are not just zero. They don't cancel completely.
I
So
see. That's why. So in this work that you were mentioning in 2009, you wrote down this system of equations that allows you to calculate this something called anomalous dimension of operators, and this system of equations, if I'm not wrong, I think it's called the Y system, right? But the thing is that you had to write down that system to find out the anomalous dimension for operators that are short, right? Which means that you write down the number of operators, and the number of operators is not large in the number of fields, sorry, it's not large in the operator. And you found the the anomalous dimension for something called the Kunishi operator, which is the smallest one, right? Now
yeah.
for large operators, right, which have a huge number of fields, there is something called asymptotic Bethe ansatz that can give you the anomalous dimension. So that's something that comes up again and again in these kind of studies. So can you tell us that what is Bethe ansatz and what is the asymptotic Bethe ansatz?
Okay. So like I said, to say that to have a so you have this string, and the string is a piece of rubber, right? A piece of string, really, right? And imagine you want to visualize a piece of string. So the simplest way to visualize is to make it very big. So you stretch it a lot and you make it huge. Now, if you have a huge string, like 1 kilometer wide, then you're gonna have a small bump on that string, like a small wave on that string, another small wave. They move 1 kilometer there for a long time, and then they hit each other and they bounce back, and then maybe they hit another one, and so on. And so you are looking at this huge wire and you are seeing some bumps of it that are moving, sometimes hitting another bump and moving, and so on. So that's a beautiful picture, very easy to visualize. But you see, it was important that the wire was huge, because then
Mm-hmm.
these bumps had lots of time to move and they were more or less free all the time. From time to time, they hit each other and so on. And so that is what happens if I want to describe strings that are very big. If the string is very big, then the fluctuations of this string, they are moving for a long time and so on. And then they are much easier to tame. And how do you tame? How do you write the state of the string? Like I said, first you say that my state has a bunch of momenta, a bunch of particles, each of them with its own velocity. But then they bounce, and now the velocities get swapped. They bounce back, boom, right? And the velocity is swapped. So you need another term in the wave function where the velocity 1 and 2 are swapped. But then 2 the bump number 2 hits bump number 3 later, and now they swap. So now you need another term in the wave function where velocities 3 and 2 are swapped. And if you go on like this, you see that your wave function needs n factorial terms if you have n particles, because you need all possible permutations of the momentum. And so if you write the wave function, which is a sum of n factorial terms, each of them for all possible combinations of where the particles are moving, that is called the Bethe ansatz. So the Bethe ansatz is such an ansatz for a wave function. Is it a good wave function? Yes, if the string is huge. Because then particles can move freely and so on. Now, as the string starts to become very small, it's not true anymore that these particles have a huge space to move. And so now, quantum effects start to be much more complicated and start to kick in. You can think like this. You can think that when particles are very separated, when particle 1 and 2 are moving, they feel each other, but they don't feel particle 3 or 4 or 5, right? Because they are very far. But now if everyone is in a small space, particle 1 and 2 feel particle 3. Moreover, particle 1 and 2, if the string is a small circle, they feel 1 and 2 from interactions that go directly, but also from interactions that go around the circle. And then there are quantum mechanical effects, virtual particles that are pair created and that go around the circle. And you can have 1, 2, 3, 4, and you have all these quantum effects. In finite volume, this is called the Casimir effect, the fact that you have quantum particles that correct energy. And now imagine you have this soup of particles, they are in a very tiny space, they are all interacting with each other, and also feeling these quantum particles, these Casimir force particles. They also scatter with those. And it's a mess. And that's why the Y system equations are more complicated than the thermodynamic, than the asymptotic Bethe ansatz equation. Because asymptotic Bethe ansatz, it's what I said before. And now as you shrink the size of the string, first, you can start taking these effects into account in a controlled way because you are shrinking it gently. But when you shrink it a lot to study the smallest possible strings, like the ones that you gave a name and correctly so, this Konishi string, which is the smallest possible interesting string, then it's not just a small correction. It's all about this finite size effects. And then you need to do what in physics we call resum. You take into account 1 virtual particles, 2 virtual particles, 3 virtual particles, 4 virtual particles, all the way to infinity, and you sum them all. You call it resum. And this resummation of the asymptotic Bethe ansatz into something more powerful is what promotes the asymptotic Bethe ansatz into the Y system. And so finding those equations was what we did in 2009. People had started studying the first effects. What happens when the string becomes smaller? What's the first effect? What's the second effect? What's the third effect? But the resummation of all of them into something that says, here it is, you can put it in a computer and plot the energy now of Konishi was what we did in 2009.
So, as you're mentioning that you solved the Y system of equations for the Konishi operator. So was it easy to solve it? How easy was it to solve it? Was it hard to solve when you were solving it?
Yeah, the equations are beautiful equations. You could make a T-shirt with them. They have some like a T shape of a bunch of black nodes and white nodes. However, solving them is complicated. It's an infinite set of coupled functional equations. You can transform them into integral equations. It's complicated to solve. So it actually took many computers to solve these equations. The first time we did it. So we solved it in Porto University with my friend Colia. So we made a script in Mathematica that would solve these equations. And the way it would solve them is, again, by a method like relaxation, like I was describing for these minimal surfaces. So you would start with the wrong solution for these virtual particles and try to make it better and better and better. And so it would iterate. And at each iteration step, the solution will be closer and closer to the good solution of these Y system equations. And we wanted to do it as you change the coupling. For each coupling, you wanted to solve these equations because you wanted to study really all values of the quantum parameters. When the quantum effects are very small and n equals 4 is very easy. And when the quantum effects are very big and string theory is very easy, all the way in the middle. And the bigger the coupling is, the more quantum effects are stronger, the harder it is to solve these equations. So what we did is we went to Porto University and we had a USB pen and we were putting this Mathematica script in all the computers of the university. So it was very manual. It was not like a cluster or something. We were really going to like 40 computers. And we started in the basement where the crappiest computers were. And there we put the points that the coupling was smallest. So it would be easiest to iterate those equations all the way to the fourth floor where there was the computational computers that professors would use. And there we put the strongest values of the coupling, the highest values that would take longer to iterate. And then Collier did this amazing script that as the equations would iterate, they would send where is the value of the energy. It would send it online to a plot where we would see all the energies of all the computers, all the 40 computers, all the 40 points moving in real time. Each time the equations iterate one more time, there would be a beep. Actually, we had a noise in Mathematica, beep, and the point would move. And that was spectacular because we saw all these 40 points moving, and then they were moving in this plot, and we had a dashed line there in the plot. And the dashed line was what? The dashed line was, if this is going to work, all these points, when the coupling is big, they must go to this dashed line, because the dashed line is the energy of classical strings, and that is what it should be. So eventually, when the coupling becomes strong, it better behave as a classical string if this ADS CFT is working and if holography is working as it should. And so when they started, these points were very far from this dashed line. They were like 3 times as big as the dashed line. It looked, oh my God, this is not going to work. Our equations are wrong and so on. And then I remember I was watching Dr. House, this TV show with my parents. The computer was nearby. It was in the evening, and there would be this annoying ping, ping, ping. And I would look, and the points, they start getting closer and closer to the dashed line. At some point, I'm calling Collie. Oh my God, it's going to work. And so I can't believe it. And indeed, at the end of the night, we were super excited that all the points were going to the dashed line, and we had seen the quantum effects and how a quantum theory, as the quantum effects become bigger and bigger, starts behaving like a string theory. So that to me was...
So you said 40 points. Did you use 40 computers to solve this?
Yeah, we used 40 computers.
So did you get permission to use all the computers at once? No one else was using
No,
the
no,
computers?
it was July or August, so no one was at the university. So we just entered there. And so we used all the computers. But people like me in Porto. I think they would allow me anyway. But
Sure.
it was holidays, and no one was paying attention. So we just used them all the computer rooms and so on. There was no one there. So yeah, no permission. Now this took, as I said, 40 computers all night with ping, 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 ping. And now it can be done in 2 seconds in one computer, all these plots and so on. Because now this Y system, which in principle is the solution to the spectrum, is old technology. Now Kolya, Gromov, Kazakov, and collaborators improved it more. They took these equations and they simplified more. Now the state of the art is not the Y system, is the quantum spectral curve. The results are the same. If you plot the energies, it's the same, but it's much more powerful. So this quantum spectral curve is really a Ferrari, whereas the Y system was
Actually, that was my next question, that
a car
you
that is
use.
not a Ferrari. Sorry?
I was going to say that this was actually my next question, that, even in the paper that you wrote, in 2009, you're using an algebraic curve, and now you have used the word quantum spectral curve. So what is this curve? I mean, what does this curve represent? And if I'm not wrong, I think it uses some cosets. So if you want to go into the details of that, you can go. But if you don't want to, I understand. It's fine.
Yeah. So uh, um, yeah, I'm taking time to find the level where I should aim at. And so maybe let me try to be not to worry about this. And then you tell me if I should clarify something. So
Sure.
in mathematics and in physics, there's something called the Riemann surface. So for example, if you ask what's the Riemann surface of a function like square root of z, it's a 2-sheeted Riemann surface because square root of 4 can be 2 or minus 2. So it has 2 possible values. And so there is a 2-sheeted surface. For square root of z, if you go around 0, you go from the first floor to the second floor, to the second sheet. And so if you want to describe the function square root of z, you should say it's a function, it has two sheets. On the first sheet, the square root of 4 is 2. In the second sheet, square root of 4 is minus 2. And if you want to go from one sheet to the other, go around 0. And that's how you go from, like in a parking lot, you go around and you move from one floor to the other. So square root of z is a curve. It's a very easy curve. It has two sheets, and going around 0 is what makes you go from one sheet to the other. If you want to go clockwise, you go down, counterclockwise, you go up. And that's it. Now, so in physics, often more complicated functions appear. Instead of square root of z, you can have square root of z times z minus 1. Now the point 0 and the point 1 are important, and you can go to the second floor if you go in the middle of point 0 and 1. But it's still very easy. There are still only two sheets. Sometimes you have functions that have many sheets, and you have many more places that you can go, and that in general is a Riemann surface. But it turns out that now let's go back to this problem of these particles moving on these small strings, and you could describe to describe now these particles. There are not like one or two particles, because as I said, these quantum effects are very, very strong. So all these virtual particles, these Casimir force-like particles that are moving around are there. So the proper way of describing the system when the size is very small is more like saying, what is the density of these quantum particles? So you have some functions that are these densities. And these functions, if you ask, what are they as analytic functions? Are they some boring functions or are they interesting functions? And the answer is they are very interesting functions. They are functions like the square root, but much more interesting. They are functions that have a cut, not between 0 and 1, but between minus g and g, where g is the coupling. But if you go through this cut, you see another cut. And then if you go through that cut, you see another cut. And in fact, there is a ladder, an infinite ladder of cuts. And when you go through each of these doors, you go to a different sheet. And then on that different sheet, there are infinitely many doors. And so it's like an infinite palace full of doors that you can go into. Sometimes you enter one of these rooms, and instead of having infinite doors, you only have one door. So this is what they call these beautiful, beautiful sheets. So there are some sheets where you enter, oh, there's only one door. And then in all other sheets, there are infinitely many cuts, infinitely many doors you can go into. And so it turns out that they found that instead of describing these integral equations that describe these densities, you could describe what are these functions analytically. What happens when you take one of these functions and go across one of these doors? And you can imagine function number 1 grow across this door becomes function number 2. Function number 2 goes around this door becomes function number 3. And instead of describing a set of equations, an infinite set of equations that we were solving in these 40 computers, you describe instead what are the rules for moving in this big infinite palace. And this is the quantum spectral curve, is this infinitely sheeted curve where you have these doors whose size is related to the quantum coupling of the theory, and you go through these doors to go in these various rooms.
Mm-hmm.
And it turns out that instead of describing all these infinite rooms, you just need to describe the rules, what's called the monodromies. What happens when you go
Yes.
through a door? And this monodromies, just figuring out these monodromies, there are not that many. Instead of infinitely many, there are maybe like 4 or 16 or 256, depends how you count. But there are a few, finite number of them. And they understood that they reduced everything to these few monodromy-like objects and these few densities, that once you solve them, then you are done. All other infinitely many quantities you get for free. And in particular, the energy, you can see it by going to one of these rooms that only has one door and going to infinity in that room, and the energy is there at infinity.
So finding these monodromies is easier than solving all the equations.
Yeah, it's much easier. Yeah.
I see.
So
So my
that you
next
can do in seconds, whereas the other equations you needed hours.
I see.
Yeah.
So my next question is regarding um, a particular set of techniques that you use. So before asking that question, I think we should clarify what that particular set of techniques is. So one thing that people use a lot when they're studying integrability and holography are matrix models. So what are matrix models?
So um, so So first, maybe let me just say, a matrix is a table. It's just a list of rows and columns full of numbers. We say, for example, a matrix, a 10 by 10 matrix is a table with 100 numbers, 10 times 10, right? Yeah. So that's what a matrix is. A matrix is just a table of numbers. And these matrices, what they can do, what you can do with this table of numbers is use them as linear operators. You can take one of such tables and multiply by vectors and use these matrices to act as linear operators on vectors. Okay, so that's what the matrices are, and the fields in nature sometimes they are matrices, like gluons. We describe them by matrices in the real world, 3 by 3 matrices. And when you have a matrix, as I said, it's a linear operation. It's an operation that rotates the vector. And these matrices, when you multiply two matrices, it's like doing an operation twice. You do it once and then you do it again. And the order matters. So if you have a matrices and you multiply many matrices, like you are doing many operations, but the order matters. And so, for example, you can imagine having these gluon fields, and you can have a gluon matrix 1, matrix 1, matrix 1, matrix 1, matrix 2, matrix 1, matrix 1, matrix 2, and many matrices. And that describes the big sequence. And it's like a line, because it's first this, then this, then this, then this. There is a line structure to it. And these operators, as I said, they appear in quantum theories, like these n=4 super Young-Mills. And you see that by multiplying many of them, we construct a linear object like a string. And that's not a coincidence. It's because everything I said about strings, I could describe in terms of operators of the theory with these matrices, multiplying many of them. And big strings are big operators made of many fields. That was something that you mentioned at some point, right? That you were saying that asymptotic bit ansatz works for big operators. That's what they are. It's operators that have many of such matrices. But then in n=4 super Young-Mills, what we are describing is these matrices, but not only that, these matrices are at some locations in space-time. And so to describe quantum electrodynamics, we are describing matrices, these fields that are matrices. And the crucial thing about matrices is that the order matters. It's like you multiply two of them and the order matters. So it's not commutative. It's not like usual numbers. And so matrices is crucial and space-time is crucial. Matrix models is when you throw away space-time. You just say, I keep matrices, I'm still dealing with matrices, and I'm still studying my fields, my quantum fields that are matrices, but I will ignore space-time for now. I will try to study just models that are just the matrix, the backbone of these theories. See that this thing that I told you before, that you multiply many such matrices and it looks like a string, that's true whether or not these matrices depend on the space-time points, right? You just multiply many of them and look like a string. So studying these matrix models is also, it's a toy model. They are simpler than the usual theories because we threw away space-time, but they still capture a lot of these string dynamics, and they can still tell us a lot about, not surprisingly, they are still related to integrable theories often. So, so matrix models, you can, in first approximation, are like physical theories that describe the strong force, where you throw away the space-time.
Okay, I see. And what kind of techniques do people use when they are, studying matrix models? And I'm talking about techniques which are not used in, usual field theories, for example, like quantum electrodynamics, for example.
So again, matrix models, you can separate them into two groups, solvable and not solvable. The solvable ones you can solve, and the non-solvable ones you have to put in a computer. When you put on a computer, what does it mean? It means that when you are doing a path integral, which is what we do in quantum mechanics, we sum over all possible fields, you are summing over all possible matrices. And then, when you are putting it in a computer, you are using, for example, Monte Carlo, which is a way of randomly picking matrices, right? Simulating these matrices. And you are summing over all possible matrices to describe the quantum path integral that describes this theory. That is exactly the same as what we do in field theory for realistic cases. But in field theory, you have to do it not only for the matrices, but for each matrix, for each point in space-time. So you have to break space-time into some grid and say, I will replace space-time by maybe 100 by 100 grid. And at each point of the grid, there is a matrix, and I integrate over all the matrices, and I do the path integral like that. In that sense, matrix models will be the same as usual field theory, more or less. You have to integrate numerically in a computer, except that you don't need to do it one for each point of space-time, because there is only one point of space-time. You threw away space-time. But it turns out that then there are theories that we can solve exactly. That actually is not only common to matrix model. There are theories that are exactly solvable, like we said before, like integrable theories, or like free theories. So those theories will be exactly solvable. Matrix models, it turns out that there are often theories that are exactly solvable in matrix models, even if they are very strongly interacting. And so the key technique that or there are many techniques, but it turns out that when you have these matrices, what really matters most about these matrices are the eigenvalues of the matrix, not really the matrix itself. As I said, the matrix, if it's n by n, it has n square elements, like 10 by 10, it has 100 elements. But the eigenvalues of the matrix, there are only n of them. And so the key challenge in matrix models is, can you separate the angular variables from the eigenvalues? And can you integrate out the angular variables? Can you get rid of them and reduce the dynamics of the matrix model to the dynamics of the eigenvalues? If you can, then you can solve the theory, because that was a huge improvement. You went from n squared degrees of freedom. Imagine n is 100, then it's from 10,000 degrees of freedom to n to 100. So that's huge improvement. You reduce the number of degrees of freedom from n squared to n. When you can do it, it's almost always guaranteed that you can solve it. And what does it mean to solve? You have these n eigenvalues. N is still very big. Typically in these matrix models, we are interested in very big matrices. And the proper way of describing these eigenvalues are with densities of eigenvalues. And now we go back to the same story as before. This density of eigenvalues, what are they? And they will be again similar to these square root formulas that I said before. They will again describe some algebraic curves and some quantum curves. And the techniques that we use to study matrix models, in the end, often have a big similarity with the quantum spectral curve that I said before. Except that the quantum spectral curve is much, much richer. It has infinitely many sheets and infinitely many cuts. And in matrix model, typically it's a finite number of sheets and finite number of cuts.
I see. So when you study these matrix models, do you assume some property for the matrix? For example, the matrix is like Hermitian or unitary and things like that. And what are the reasons to assume those properties if you assume them?
For example, you could say that if I have a theory in space-time where these properties came from some physical principle, like hermiticity is often required to have a unitary theory where observables are real and so on. And then you say, I want my matrix model to be a toy model for the universe. Then you try to keep some of those properties. You want things to be real, you want distributions to be real, and so on. It's not crucial. You can integrate over matrices that are not real, and so on. Let me maybe mention something. In quantum mechanics is all about these path integrals. Namely, in quantum mechanics, everything that can happen happens, and you have to sum over all possible things, and you have to integrate over all possible stories. This could be stories of particles moving in space-time. It can be stories of these matrices. It can be stories of the strings, what shapes they draw, and so on. And when you sum over these stories, which means integrate over these stories, there are extreme stories. For example, the matrices, they can be very big. The numbers in the matrix can be huge. And then when you say, what weight do those configurations have? If that weight better be very small. Otherwise, this path integral is not going to converge. And so often we have these conditions on the fields that we say the fields, when they go to infinity, they must decay, or the matrices cannot be too huge. And sometimes, for example, we say the matrix is Hermitian because then the eigenvalues are real. And then it's easy to construct some weights that are going to suppress very big eigenvalues, right? You just put some term like minus trace of m squared. Minus trace of m squared, if m is an Hermitian matrix, in the exponent, that's exponentially small and m is very big, right? So e to the minus. So you can write confining terms. If you tell me m could be I times an Hermitian matrix, now this path integral makes no sense because now it's not convergent anymore or something like that. And sometimes, even when you write the same path integral, it can have more than one definition because if you look at some function, sometimes the contour of integration matters, not only where it goes at infinity, but the way you go to infinity. And that is something that matrix models are also a good lab to study. Sometimes people define some matrices like some ID function-like matrix models, which is like a model where the interaction is like instead of x squared, it's x cubed. And if you think of x cubed, naively, x cubed is bad because e to the minus x cubed is very small if x is very big. But if x is very big and negative, it's not very small. It's the opposite, right? And so you cannot go to very big negative x with e to the minus x cubed. So you have to go in the complex plane in some complex direction. So you can go from to plus infinity, but when you go to the left, you cannot go to minus infinity. You need to go at some angle, e to the 2 pi over 3, something like that.
I see.
But which angle do you go? Do you go up or do you go down? It's up to you. You choose. And you have more than one definition. And is it the same? No, not exactly, actually. And there is a small different imaginary part. And these matrix models, because they are exactly solvable, they are a great lab to ask, could these questions also be relevant for us? Could it be that you give me a field theory, and perhaps there is more than one definition to interpret that field theory? Depends exactly what do I mean? What's the contour of integration for my fields and so on? These are subtle questions, if you want, about foundations of quantum field theory that field theory is so hard that there is these often are just questions at the level of ramblings like this. But some in matrix models, they can often be made precise, and then this can give us some inspiration for how to try to make them precise in field theory.
So the question that I wanted to ask you before, I ask you about the matrix models, was that there was this paper of yours that deals with something called huge operators that are related to objects with incredibly high energies that they back react on space-time. When you write down the equation that comes from the matrix model, it looks like a hydrodynamic equation. So I wanted to ask you that does it happen often that the equations that you get in holography are like fluid mechanics equations?
There are instances of the equations becoming fluid equations. Typically, there is some physical reason for that, and it can be understood physically. What is the fluid? The fluid could be some fluctuations of the horizon of some black hole, and we can understand why these fluctuations should be governed by something like a fluid. This fluid that we found in this work with Arish, Murali, and Kazakov were different. This was a fluid that was known in matrix models, but to my knowledge, not used in holography. So this fluid is the following. Suppose you want to compute a very simple object for people that know algebra, which is determinant of exponential of xi yj. So you see, it's a matrix whose entries are exponential of xi yj. So x1 y1 for the first element, x2 y1 for the second element, x3 y1 to the third element, and so on. So each element of the matrix depends on one x and one y, and you just fill in a very simple n by n matrix with this exponential of xi times yj. Okay, where I runs from 1 to n and j runs from 1 to n. What are xi and what are yj? They are just numbers, n numbers, they are the x's, and n numbers, they are the y's. And the x's are distributed in some density, and the y's are distributed in some density. Now, beautiful result, which is compute this determinant, the product of the eigenvalues of this matrix. The way to compute this determinant is the following. Imagine these densities these two curves, these two densities, as the densities of a fluid. See, out of the blue, fluid comes in. And now this fluid, the fluid for density x, needs to go to the shape of the fluid for density y in 1 unit of time. And this fluid has some given pressure. It's a fluid that is compressible, and there is some negative pressure that wants to compress. So you need to prepare the initial fluid velocity in a way that it's going to move from x to y. Compute the action of this fluid. That's what the determinant gives. Okay. Now, this is a true statement. It's just, you can think it's just a mathematics. Determinant of such simple determinants. If you ask, how does it behave when the matrix is very big? The answer is, it's like a fluid. So that's just mathematical statement. That implies that some quantities in holography, like some interactions of some very big operators, are given by a bunch of fluids. You don't have just one determinant, you have a bunch of them, and so you have a bunch of fluids that are moving and meeting at some point. So it's like some tubes of fluids that there are some junctions. So it's like some network of tubes of fluid.
I see.
What is the meaning of these fluids? What is this time, this unit of time that the fluid moves? I don't know.
Okay, I see.
So it's a mathematical statement that these very big operators, effectively, their computation of their quantum correlation function translates into the computation of these determinants. It's another fact that these determinants are given by the fluids, and combining these two facts, it turns out that these interactions of these three huge operators, in the end, what I have to do to study it is solve some fluid equations. So this is something done purely in the quantum theory. I start with the quantum theory, step 1. Step 2, I understand that because of supersymmetry, the result is not 0, but lots of things cancel, and I can turn off most of the terms, right? So that's related to what you asked in the very beginning. Shouldn't most things cancel? And indeed, they do. And in this case, many things cancel. And so much so that for this case, everything related to space-time cancels. And so I can drop space-time. And because I drop space-time, what do I get? I get a matrix model. And now I'm studying matrix models. And I have these three huge operators in matrix models. And then there is this beautiful relation to fluids. And therefore, from the quantum theory, no quantum gravity, just from the quantum theory, we predict that the interaction of these three huge operators should be dual, should be given by some fluids. And now you ask, what about in quantum gravity? How do you describe this in quantum gravity? And these should be some very complicated solutions of Einstein equations. Because putting these huge operators, because the operators are so big, what is going to happen is that they are so big that they deform spacetime. Like a very big planet creates a gravitational field. These very big operators are like, instead of a string, they are like a gazillion strings. They deform spacetime and they deform it. And so you have three huge operators. They deform spacetime in three different ways. And this needs to be all some solution of supergravity equations. And that solution, somehow when solving that supergravity equation, it must be that this fluid will show up. And it must be that this fluid will somehow appear in solving this. But if you want, it's like a prediction of quantum theory. Quantum theory is telling people that do geometry, that do gravity. When you will go and try to look for these geometries, mathematically, when trying to solve these Einstein equations, you are going to find some fluid equations. And it's a hint. Now, did people find this from gravity? Not yet, because no one managed yet to find these solutions of Einstein equations. Yeah, I need to find some supergravity experts that I can try to convince to look for these solutions. Yeah.
I see. So another topic that you have worked on in the past is Bootstrap, right? And one of the aims to pursue this program is to understand the space of quantum field theories better, right? So can you tell us a bit about what is the idea behind S matrix Bootstrap and conformal Bootstrap, and what are the major aims, and how do you probe the space of quantum field theories using this program?
Yeah. So the Bootstrap, you can think a bit, it's like more or less the extreme opposite of most things that we spoke so far. What we spoke so far was about trying to extract exciting physics by solving particular theories. So there is some theory where I can relate to some fluid, I can solve this fluid, excellent. There is another theory where I have some minimal shapes and I can try to use integrability of these minimal surfaces to solve it. Or some quantum algebraic curves that come in the spectrum of, because the theory is integrable and we can tame this quantum interaction. So that's one approach to physics, is try to find examples where you can solve things exactly to learn about physics. An extreme opposite approach is to study the space of theories, is to say, let me not try to focus so much on one very special theory. Let me try instead to go the extreme opposite. Let's ask, what is the possible space of theories? What could be the result? What could be, for example, I could go, it's not been done, but I could go to these minimal areas and ask, in a general theory of surfaces, what would be upper and lower bounds on these minimal areas depending on different actions. And I don't commit to a particular theory, to a particular theory of soap bubbles. I just study the general theories and ask, what are possible bounds? So this idea of Bootstrap is the idea that you set up the rules. You say, I want to study, for example, scattering of particles. That would be the S-matrix Bootstrap that you mentioned. And you say, what are the rules? The rules is the theory must be unitary, it must be Lorentz invariant, it must be causal, it must be the amplitudes we assume are analytic functions. So you make a list of what we would call sacrosanct principles, like these ones for sure, I believe. So principles that come from quantum mechanics, from relativity, and so on. And then you ask, compatible with these very basic principles that we have no doubt are there, what is the possible space of scattering outcomes of experiments? And then you're not getting a number, but you are getting bounds, you are getting shapes. If you are studying many parameters, like three parameters, then you get some shape in 3D space. And instead of studying, therefore, particular theory, you study these shapes of what's allowed and what's forbidden. And the key thing that typically we do then is look for the most valuable real estate in this space, is to ask, does this space have particular features? For example, suppose you ask what's the allowed and forbidden space, and you get some space, some potato, but the potato has some tiny tip at some point. Then you would ask, what's this tip? What is the theory that lives at the tip of this potato? I mean, it must be a special theory. Why is there a tip here? And so that's what we do in the Bootstrap study. We carve out, often with computers, often analytically, what's the possible space of theories. This space of theories, excitingly, is not boring. It's not like a ball. Instead, it has lots of structure, like cusps, ridges, and so on. And then typically we ask what theories could live at these ridges. And in particular, we would like to ask, could our universe like to live in the boundary between what's possible and impossible? Could it live in some of these spaces of the boundary? If our universe is at the boundary, then this Bootstrap could be a way of finding it.
So one thing that you just mentioned is a bit related to my, a question that I wanted to ask. So you said that there are these parameters, right? What kind of parameters are they? Are they couplings or something else?
So that is half of the fun in this project, in this Bootstrap thing, is what are the quantities, what are the x's, what are the parameters? If you see, the outcome of experiments is an infinite dimensional space, because you can scatter, say, electrons at 1 giga electron volt, 1 mega electron volt, 1 tera electron volt. You can look at the outcome with one angle, another angle, another angle. You can scatter 2 electrons and study the outcome with 4 electrons. So it's an infinite dimensional space. To describe a scattering experiment, you need infinite amount of data. So what 3 numbers do I choose? Well, in this infinite dimensional space, it's like I'm looking at a section, and I'm hoping that that's also what we do in all fields of science, of sociology, for example, right? We also decide to pick some axes that we believe are the important ones. So that's an art, picking what could be. So a particular example are couplings, like you mentioned. So couplings, it's a bit like interactions, like how electron interact with photon. There is a coupling between electron and photon, right? So you study string compactifications, right? So you have couplings, like Yukawa couplings and so on. So couplings would be an example. You could try to ask, I don't know what my theory of pions is, because we don't. It's an example of strongly coupled theory. But there is some coupling between pions and the rho particle. And what is the possible value of that coupling?
I see. So if there, if you think about the space of all quantum field theories, if somebody naively asks the question that what are the coordinates of this on this space, one possible answer is couplings. But is there some other answer apart from that?
Yeah, a very useful space of coordinates are the low energy parameters. Namely, for example, suppose you scatter gravity. At very large distances, we know the result. It's just Newton's law. We know that particles at very large distances, which means at very low energy, the result is universal, and it's what gives Newton's force between particles. But then, as the distance is becoming smaller, in other words, as the energy is becoming higher, there is the first correction to Newton's law, and that is parameterized by one number. And then as it goes inside further, there is another correction, and that's another number. So in more technical terms, this would be the coefficients of the irrelevant operators. And so nice coordinates that you can use are these coefficients of these first corrections to the low energy universal physics. So when you those are particularly nice ones, because if I were to have a very powerful accelerator that will measure deviations from gravity, right? When we want to UV complete gravity and we scatter gravitons, the first correction to Einstein gravity will tell us about the first correction that maybe comes from string theory, maybe comes from another theory. But the UV completion, the first sign of the UV completion comes in these low energy deviations from the original theory. So those could be nice parameters if you can see how big or how small can these first corrections to Einstein gravity be, for example, in the case of gravitons.
I see. So you just mentioned that there are some, interesting features when you study these spaces, of quantum field theories. So if you want to study the geometry of this space, shouldn't we have a metric on this space? Do we know what kind of metric we can put on this space?
Right. So that's an excellent question. And probably there are people that would give better answers than me. So let me try to say a few things, but I'm sure that I will be missing some very basic stuff. So the question you could ask is, how are field theories organized? So how is the space of quantum theories organized? Why do I say that some theories more or less the same as another, but some other theories very far away? So the conventional way of organizing theories is according to the renormalization group. So we say that, for example, we can have theories that look very different when we look at them in the microscope, but when we zoom out, they more or less look the same, right? Like you can have many liquids that look more or less the same, but if you look inside, Coca-Cola and water are very different, right? Okay, they also look different from the color point of view. But you can imagine liquids that have the same color, but they are made of very different stuff when you zoom in. But but effectively they behave the same at low energy. And so that is an example where you would have different theories, different microscopic theories, and you could say if at low energies they give the same thing, I would say they are close. So then you would put together all liquids that give more or less water close by, but materials that microscopically give a solid. Instead, you say these are very different beasts. And so that would be a way of putting theories together according to the renormalization group flow, according to what happens to them when we go to when we zoom out or zoom in. Because when you do this, while there are infinitely many theories, because it's like you have infinitely many materials, you can put different molecules and so on, the number of fixed points, the number of possibilities at low energy is actually finite. There are only a few. that's remarkable, right? It's an amazing thing that there are not many things that can happen at long distances. It's why physics is so powerful. It's not like there is there are a gazillion theories of gravity. There's only one because there's nothing else you could write. I mean, this is just fascinating, right? It's amazing. If you want to study Newton's law, it's inevitable. It's the theory. It's the only theory at low energy, right? So that's fantastic. And but at high energy, when you zoom in under the microscope, there are many possible what we call UV completions. So those UV completions would all be close if they describe the same Newton gravity. But if instead they describe Young-Mills or electromagnetism, then they are far away. And so these fixed points, those we know how to put metrics on them sometimes. At least people that study conformal field theories know how to put metrics on this conformal field theory. There is a homological metric, and there are some possibility. When we are describing gap theories, my understanding is that yeah, I don't think we have a good way of putting metric on quantum field theories in general.
Okay.
So I think if I have some theory, I don't know, glue balls in nature, they have there are a few stable glue balls in the real world, like 3 or something. If you give me some other theory, yeah, what's the metric in theory space? So people would say that probably they would say that if you can deform continuously one theory to another, at least they are relatively close. Sometimes you cannot. Sometimes in going from one theory to another, you need a phase transition. For example, the number of particles might change discontinuously. Instead of 3 particles, now you have 5 particles in another theory. That probably is not a theory that's very close if the number of particles changes.
I see.
But how to quantify this when you have this 3D shape? Yeah, I don't know if there is a mathematically well-posed answer to that. Of course, if you tell me the coupling is 1.3 in one theory and it's 1.29 in the other, I would say, okay, they are probably close. But it's a very naive answer. I mean, it's maybe that coupling is close, but many other things are very different. I'm not sure we know to quantify that.
Oh, okay. I mean, but do you think that if we ask more topological questions, for example, do you think that the space of quantum field theories is connected, or is it disconnected? Does it come in some parts? What would you say? And do we know if it is connected or not?
We know that the space of conformal field theories, for example, is not connected. We know that conformal field theories are very special and they occupy typically isolated islands that are really disconnected. So when people were studying these conformal theories using these bootstrap techniques, they found an island around the Ising model, an island around the O3 model, around the O4 model, and so on. They call it the bootstrap archipelago. Now, that is for conformal theories. Now you say, what if I introduce a scale? Can I now go out of these islands, go up, and then after going up, go down to another island? And yes, the answer is probably yes. In that sense, probably most, I don't have a good reason to believe that the space of theories is not connected. But it depends. Are you allowed to change the dimension of space-time or you fix? Probably you fix. Okay, let's say you fix.
Sure.
We are in a fixed number of dimensions. And then you have the freedom of changing all the parameters and so on. I'm not sure. I suspect it's connected, but I don't have a super strong reason for saying this.
Okay.
But conformal theories, as I said, we know it's not. We know that there are isolated theories. There is a special theory, and then there's another special theory, and there's nothing in between.
Yes.
That we know for sure. But as I said, they could come from different microscopic models. And once you go to microscopic models, it's like doing engineering. Now you change in a lab the material in a continuous way, and then you send it away. And now when you zoom out, it's a different material. So I think if you are allowed to zoom in and then zoom out again, probably they are continuous. I don't see why they would not be.
So even if we don't know what metric do we put on the space of theories, do you think that we have any reason to believe that there is a unique metric that we can put, or do you think that we don't know about that?
Uh, no, unique, probably not.
Okay.
Probably it's not unique, but what is a theory? A theory, it depends. So some people would say a theory is, for example, in particle physics, is the set of all possible scattering outcomes. In other words, all possible S-matrix elements. So then I give you a list of scattering outcomes, another list, and you want to say if they are close or not. You don't care about Lagrangians, you don't care about path integrals, you don't care about how I got these numbers. You just care about what are the amplitudes, what are the scattering outcomes in theory A, what are they in theory B. And then I think probably you can cook up a simple scalar product, a simple coupling between these two objects that makes sense. But probably there's more than one, right? I mean, you can subtract the square of them, subtract the fourth power of them. There are probably different ways of saying if these are close or not. That I doubt is unique, but you can probably come up with nicer ones that as you change scales move in a nice way, or some metrics that are more friendly, that you study them at some energy scale, and if you study them at other energy scales the result is more or less the same, right? Because that question is also very energy dependent, right? You could have, for example, two theories are the same. If it's at low energy, it's one thing, right? Because at low energy, as I said, there are not that many things. So many theories will look the same at low energy when you scatter. All theories of quantum gravity will look the same at low energy, but they will all look very different at large energy. So do you want what do you want your metric to get? Depends. Maybe it's probably an energy dependent metric that depends on the energy. Otherwise, it's useless, right? Because
Agree.
so you want it to depend on energy, but
Yeah, it makes sense.
roughly you
Makes
just
sense.
make the difference of the scattering outcomes and square
Sure,
it.
sure, sure.
You define that as the metric.
Sure, makes sense. Okay, so I have one more question, and then I have some people's questions, that sent, questions to me when I announced this podcast. So one question that I have is that, are there some features, or are there some, what should I say? Yeah, I think features that you consider before taking a PhD student. So, what features do you look for when you take a PhD student?
The main one is independence and not being afraid of bugging me and harassing me for my time. Turns out that I have many projects going on, and I need my students to write me. Typically, we have this Slack channel that we use, or Zoom, or email, or whatever. And maybe I'm traveling, maybe I have another meeting, and I just don't reply. And what I cannot have is a student that once I don't reply, that they just give up. So I need them to write me again the next day or the next hour, to write me on Slack again. So that's the main thing. They cannot be shy in writing me on chat or on WhatsApp or something. So if they have this attitude that, oh, maybe his time is important, maybe I'm imposing, that is the worst. And especially because when you introduced me, as you mentioned, I spend roughly half of my time in Canada, half in Brazil. So I cannot, because I'm split between the two, I need the students in Brazil to keep writing me when I'm in Canada, and the students in Canada to keep writing me when I'm in Brazil. Often they come back and forth with me. So the ones that are here in Perimeter, they visit me when I'm in São Paulo for a few months of the year, and vice versa. But and that helps a lot, of course. That's crucial. That's another thing that if a student hates this idea of moving around, that's a very bad idea also to work with me. But I would say the main one is not being afraid of harassing me. If the student is not afraid of harassing and is excited about the work, then I'm happy. Then it's great.
I see.
You need excitement and not being afraid.
I see. Okay, so I have some people's questions now. One question is that, Do we expect that using S-matrix bootstrap, we can eventually solve the real-world QCD? By solve, I mean get all the mass of the resonances and the coupling constant. If the answer is yes, should we also focus, what should we focus on to make this happen?
So in this Bootstrap program, there's always a tension between what you put in and what you get out.
Mhm.
So if I just say, I want to study the space of all scattering experiments, then that's very vague. Then I cannot distinguish studying QCD or studying gravity or studying, I mean, there are so many theories, so many different physical theories. So I need to be more specific. I need to start injecting information that tells me that I'm studying the theories of QCD versus theories of gravity versus other things, right? And then there is the question of how much information do you input? Do you say, I want to study the space of theories, knowing that my theories have these three glue balls with these three masses, and then you get the other ones for free, or you don't want to put any information? And so that we don't know this game. So what we see is that if you inject some of the data that comes from experiments in this game, you get other of the data for free. The more data you inject, the better is this. But then it becomes dirtier, right? If you put lots of data in, then you'd say, oh, it's not so surprising that I get some of the missing data out. I want to the goal is always to put the least amount of input and get the most amount of output. So I think the answer is, depends on how much you are willing to commit. If you are saying, I want to impose that my theory is asymptotically free and nothing more, then the answer is certainly no, because we now know there are many theories that are asymptotically free and have pions and so on. It's not like there is one. There are many theories. That was actually the problem with S-matrix bootstrap in the 50s and so on. They were asking for too much. They were thinking, I will just think and write the analytic properties of amplitudes, and I'll be very smart and I'll fix everything. And that's guaranteed to fail, because there are many theories that can do, right? That's what we learned when we started learning about quantum chromodynamics and perturbation theory and consistency of all these theories. We saw things are not unique. There are many possibilities. So you need to inject more. You cannot just say, I have a QCD-like theory. What is the mass of the glue balls? The answer is not unique, for sure.
I see.
So, but there is a chance that you don't inject much more and that you get very nice results. So that would be the hope. So Andrea Guerrieri, for example, is exploring a lot this type of direction. And recently he tried to inject the most. Namely, he said, what's the space of S matrices that are best compatible with all the scattering data we have? Say for pions, for example. Take all the pion scattering data and now study what's the space of possible pion S matrices that are as close as possible to this measured experimental data.
I see.
And this data goes in some energy range, the energy range of the accelerators that we did. And when you try to fit all possible scattering amplitudes to this data, he found that in one particular channel of some spin 2, I think, a channel, some isospin, whatever, that there was a new particle there at some energy not yet measured. So he made a prediction with collaborators that there probably is some kind of tetraquark at some energy not yet explored. So, I mean, if that's measured, for example, I think it's an example of the bootstrap giving you a hint of a new particle, for example.
I see. So one question is that what is the research atmosphere like at ICTP Cypher?
Sorry?
What is the research atmosphere like at ICTP Cypher?
The research? I could not understand, sorry.
The research atmosphere.
Atmosphere, sorry. No, it's great. In all physics institutes, I think the research atmosphere is similar. You have lunch with colleagues that work on similar things, but not too similar. And that's when you discuss typically physics of what papers came out today and different areas, and you see if different ideas from different areas could be relevant for yours, and you get inspired. And then you go back after lunch, and then you discuss with one or two people that are working on the same things that you are working on, and then you really try to push really your projects. So as long as you have a critical mass, it's not like you need a perimeter is a top luxury, right? I mean, perimeter, like hundreds of people and so on. So it's from that point of view of being able to discuss many more topics is really the best. There's nothing like perimeter. But to have an amazing atmosphere, you need a critical mass. You need like 4 people to go for lunch with that work on relatively similar topics. And then you need 1 or 2 people that work on what you are working on. And so I would say I would be, from that point of view of just research, I would be very happy more or less anywhere. ICTP Cypher has one particularity that makes it a special place, which is that it's a hub for Latin America in the sense that it has many, many workshops and schools and conferences whose goal is to help all the region and to attract people for these schools and workshops from all over Latin America, a bit like ICTP in Trieste does for that region.
Right.
So that makes the atmosphere very rich as well. Sometimes there are conferences, statistical mechanics, for example. It's a topic I like very much, but it's very out of what I usually do. So then I have lots of statistical mechanics people around, and I can learn what are the exciting problems they are thinking of, and so on. So in that sense, that's a bit similar to ICTP or to KITP or other places that run programs. So it has that's a component I like very much.
Okay. So the next question is that in one of your papers called "Following Black Hole States," you followed states by varying the number of colors that you have in the Super Yang-Mills theory. The question is that the number of colors is an integer. Can you treat it as a real number?
Right. So that's a great question. And so sometimes the answer is clearly yes, and sometimes the answer is we don't know. So suppose you have some quantum effects, and we study the story of particles that are moving in space-time, and when they meet, maybe they form some bubble in space-time, like, right, you have some loops in space-time. That means that particles move, and they swap some particles amongst them, and they swap a bunch of particles. How many particles? That depends. That is related to this number of colors. Maybe the number of particles that can be exchanged is n, and n is a number, like 5 or 6 or 7. And then it means that whenever you draw a diagram for a possible story of the particles, whenever you see a bunch of these particles, you put a factor of n to indicate it could be particle 1, 2, 3, 4, 5, 6, or 7. And you put, and so therefore there is a factor of n. And if the diagram is more complicated, maybe these particles could appear in 2 positions, and then you put a factor of n squared, because one particle could appear here, one particle could appear there. And so n, in this case, is just a counting parameter. It's just a weight that shows up in the graphs. As you are summing over the stories, n is appearing in a very simple way, just weighting, saying it appears with factor 7, this graph, because there are 7 particles that could be here. This 149, because it appears in 2 places, and so on. From that point of view, making n not an integer is fine. You can say if I have 4.2 particles, I put a factor 4.2. It looks weird because normally we are used to thinking of particles as 1, 2, 3, 4, 5, not 4.2. But okay, you have to overcome that psychological barrier and you just put whatever number you want. So does it mean that I can smoothly go from 4 to 5 particles? Yes. You just change that number that you put there, n, where it was 4 and 5, instead go in small steps and put 4, 4.1, 4.2, 4.3 until you get to 5. And you will see that the result in the beginning is 4, the result at the end is 5, and in the middle it's something that interpolates between the two. And that gives a meaning to interpolating between the two, but physically you are not exactly sure what it is. But it allows you to follow the states and see which state from 4 became the state from 5. And so that's what we did in this paper. We said, I have this theory. The number of colors is related to the gravitational strength in this holography. And so by changing this number of colors, it's a bit like you are changing the gravitational force. And that's nice because it allows you to turn off gravity, and then you have a bunch of strings, and then turn on gravity, and these strings can collapse into a black hole. So it's a toy model that allows you to see what is inside the black hole, because you turn off gravity, and then you don't have gravity, and you just see. And then you turn on gravity, and poof, now you cannot see because they are inside the black hole. So that's why we call this following black hole states. Now, this
Right.
I described it when you can make sense of n, when you have these diagrams and n is just weighting the diagrams. But what about a non-perturbative definition of the theory? Can we make sense of n non-perturbatively and so on? And the answer is I don't know, because we don't know what is non-perturbative. I mean, right?
Right.
It's a word we use to look fancy when we don't know exactly what we are doing.
So sometimes when you have theories with n colors, there are expressions where you have to sum from 1 to n. So what do you do when you get sums like this? I mean, then you cannot make sense of non-integer n's, right?
No, depends. Often you can make sense of non-integer n. Let me give you an example. Suppose you are summing from 1 to n. What do you want to sum? Let's suppose you want to sum 1 over I squared. You sum I equal 1 to n, 1 over I squared. Right? So now it depends. If n is 1, it's 1. If n is 2, it's 1 plus 1 quarter. If n is 3, it's 1 plus 1 quarter plus 1 9, and so on. Right?
Right.
So now it only makes sense up to n. But now do the following. You have the sum up to n of 1 over I squared. Sum from I equal 1 up to n, 1 over I squared. Now write that as a sum from 1 to infinity minus the sum from n plus 1 to infinity. So you summed everyone and you subtracted the tail. But now go to that tail, and instead of summing from n plus 1 to infinity, shift I and sum from 1 to infinity, but the sum is not 1 over I squared, but 1 over I plus n squared. Right? Now that sum goes to infinity. In other words, you get sum from 1 to infinity of 1 over I squared minus 1 over I plus n squared.
Right.
And now n can be whatever you want.
Yeah, I mean, I agree. So the thing is that when you have
So that's an example where n before only made sense as an integer. I did a few manipulations, and now n can be whatever you want.
Yeah, what I'm saying is that when you have a function of n, of course you can have n to be anything. What I had in mind is that when I appears as a subscript, and then what you do when it appears as a subscript on some fermion, for example, then can you make n a non-integer?
For the fermion field, no. But I would say the fermion field is not something physical.
Okay, I see.
What
Makes
is
sense.
physical is like the energy of some soup. And that is done by taking the soup of fermions and summing over all possible fermions and doing these sums. And then what I'm saying is that those sums, if you have n fermions, they will produce factors of n everywhere, or sums up to n, like the ones we were just describing. And those objects can be made sense at any n.
Right.
Now, if you ask, what about the fields themselves? Before we had n squared gluons. Can I have 9.1 gluons? No, you cannot have now. What is the 0.1 gluon? That we don't know. But that's not the physical quantity asking what's the field of a gluon.
Okay, I see. Makes sense. Okay, so the last question from the people is that in your work, you use a planar limit all the time. And, there are these planar theories. Can you explain in simple words what are planar theories and what are non-planar theories? Well, not theories, diagrams, planar diagrams and non-planar diagrams. Yeah, that makes more sense.
Yeah. So planar diagrams are diagrams that you can draw on the plane. So imagine I have a graph, a network, like streets on a city. You look from the top and you have the streets, right? So they can be drawn on the plane because you look from the top and that's the picture, right? But now imagine metro lines. The metro lines often the blue line and the yellow line, they pass one on top of each other. You cannot just draw them on the plane. So the metro lines is an example of an n-planar graph, and the streets are an example of a planar graph. So both are sequence of lines that are connected between stations or between corners of streets. But the key difference is that streets are planar. You look from above and you can draw them on the plane, but metro lines are non-planar. Sometimes the metro go one below the other and so on. Now, when things are planar, there is something nice. It's that it looks like a surface, right? Because how do I describe a surface? Like in a computer game, I describe it by many, many small edges, right? And this triangulation of this surface is what gives this monster, right, that move, right, in a computer game. So these surfaces, these graphs that can be drawn on a surface are what you need to describe these shapes, surfaces. So they are what you need to describe strings like the one behind me, that when they are moving and interacting. Then we need to describe this small triangle, this triangulation of these surfaces that are planar.
Mm-hmm.
Now, if you wanted to describe, however, some object, like in a computer game that has a hole, that is not, that has a hole in it, like a donut, then to describe a donut, the surface is not a plane, it has a hole in the middle, right? The hole of the donut. Then you need what is called diagrams with genus 1, with topology 1. They cannot be drawn on a plane, but they can be drawn on a torus.
Mm-hmm.
And then if you want to describe some monster that has two holes, now you need the genus 2 surface and so on. And it turns out that often, when the number of colors is very big, planar diagrams dominate, which in physical terms means that the dual strings theories, the strings don't want to form these holes and interact. They prefer to just not interact, or when they interact, they just interact without forming these holes. These holes is like a suppressed quantum effect. So that's an example of all the things behind. Now, that's basically relevant when I'm studying string theory and single strings and so on. When I'm studying these huge operators and these operators that are big to deform spacetime, it is totally different. Because there, one string doesn't deform anything, right? I mean, if I have one string, one tiny particle moving in spacetime, it does nothing to spacetime. But when I have a gazillion million ton of particles, they form a black hole. But then I need many, many particles and all these interactions. Then it's not a planar limit anymore. So in these works of huge operators and so on, it was not the planar limit. It was a different type of limit. When we study string theory, we often study first the planar limit.
I see. I sorry, actually, I missed one last question from the people. So this is the last question. The question is that as a PhD student of theoretical physics, do you have any advice for building collaborations and networking as a PhD student?
So I have a couple of advice. One advice is try to find ways of going for lunch with people. Not you don't need to go every day to lunch with the professors and so on, but if you can find a way that sometimes you go along with the faculty and the postdocs and so on, it's very good. It gives you really a perspective on other fields. You don't want to be too isolated, just discussing with your advisor and nothing more. So I think I was fortunate when I did my PhD in Paris that we had no canteen or anything, so everyone would get sandwiches. So it was very democratic in that sense. We would just go out, get a sandwich, and go sit in the garden and eat the sandwich there. And it was all the students, postdocs, and faculty were very good. It was and it was very useful for me to get a better picture of the field. So that's one thing I would suggest. So of course, if you are in a place where people typically go to different places and so on, try to find a way that sometimes you can go for lunch with these people. And even if you just listen, it's very useful. The second thing I would say is that I found that perhaps the most valuable thing for me for my PhD was meeting my colleague at the time, Kolya Gromov. Having a collaborator that you work well with, that is your age and that is a friend, is really something amazing. It's a superpower, right? I really feel like it's not happening, but if tomorrow I'm stuck and I have no idea, or I'm desperate, or I'm bored to death and I need something, I just call Kolya and say, "Can I visit you in London? And maybe we could work on something new for." And this is really such an amazing thing. So And so try. You will not find, not everyone will be perfect match for you. But I feel like if you can find another student that you like working with and that can be a friend, that is super valuable. It's really an impressive, really a blessing to be able to have a friend that maybe you will work with, maybe not. I haven't worked with Colin in the past many years, but I will for sure work with him again eventually. And that's very, very important. I had three pieces of advice when you asked the question. So you asked what would be advices for a beginning PhD student or for a PhD student in general? For collaborations, for establishing collaborations, right? And the last thing I would say is go talk to speakers at the end of the talks. Students are not going to ask questions during talks. I mean, they don't. It's just a fact of life. Go talk to speakers at the end of talks. You have questions, you think the questions are silly, and therefore you don't want to ask them during the talk. That's fine. Of course, the optimal advice is ask questions also during talks, but that I know people don't do. So don't worry. But after the talk, go talk to the speaker. Go ask, oh, I saw this, I work on this. Do you think there's any relation between the two? Or you mentioned that it would be interesting to do this, but do you think it's really realistic? Do you think I could look into that? Because those informal conversations at the end of the talks, maybe they will tell you, yeah, I said this would be interesting, but that's actually probably too complicated. A better problem is this that I would be interested in. I actually don't have too much time. If you want to work on it, we could try to discuss. Do you think it's something that is you have the tools to solve and so on? And many collaborations can start from there and many informal discussions. It's also the time when people will give you a much more candid view on what is doable and what is not.
Mm-hmm.
Because during talks, we always say it would be interesting to do X and Y and Z, but we don't grade the X, Y, and Z. We don't say Z can be done in 100 years, Y could be done tomorrow after lunch. But there is such grading. We know very well which problems are immediate, which problems are not yet well posed, and it's something that they are more motivational than concrete problems. And so going to talk to the person after the talk in an informal way, don't be shy about that, and really force yourself to go talk to the speakers after the talk. Say, I go to this talk and I will go talk to the speaker after the talk, even if it is just to ask a clarification question, but really force yourself to do that. And I think good things will happen because you will do it like 10, 20, 30 times. And out of these 30, 1 or 2 will be very good.
Okay. So my questions are over. Thank you so much for your time. And I hope that we can talk sometime in the future as well. But thank you so much for your time. It was nice
Thanks,
talking to you.
Hassan. It was great fun. And I hope it was the right level. And I had a great time. So thank you.
It was.
And congratulations on doing this. It's a really good thing.
No, thank you so much. So if you like this video, give it a thumbs up and consider subscribing. And the YouTube algorithm thinks that you will also like this video.